Hi, everyone. Thanks for coming to this session. This session is another quantum session, and I'm very excited about the papers that are going to be presented. So let me just give you a couple of themes that you might want to look out for, pay attention to as the talks are being presented. So the first theme is, quantum mechanics says that we live in an exponential space because n qubits requires 2 to the n numbers to describe. So this is a very strange and exciting thing about quantum mechanics. And some of these papers will talk about how do we understand this exponentiality of nature, or how can we tell if nature is really an exponential place. And the second theme that you might want to look out for is how some of these papers really take ideas from theoretical computer science to really sharpen some of the concepts and intuitions that have been developed over time by physicists over the years, and really illuminate some more understanding. So let me give you a brief description of some of these talks. The first one is called Rigorous RG Algorithms and Area Laws for Low Energy Eigenstates in 1D, which is kind of a mouthful. But here's at least my understanding of it. So like I said, if you have n particles, quantum mechanics says that describing them in general takes 2 to the n numbers. But if that's the case, then how do physicists make a living? I mean, why aren't they spending all their time just writing down an exponential number of numbers to reason about physical systems? Well, if you talk to a physicist, they might say, well, physically relevant states that we encounter in nature only occupy a small fraction of all possible states. Okay, so we don't have to write down a general quantum state, and we only have to deal with a small subset of them. Nature has some very nice properties like locality and symmetry and so forth. But then if you still try to probe this question, okay, we have all these facts, but really how can we still reason about physical states in polynomial time? And, oftentimes they'll say, well, the heuristics that we've developed over the years, they just work and work very well. And it's kind of hard to argue with the results. I mean, they've led to Nobel Prizes and very successful ways of understanding nature. But for a long time, a lot of these heuristics had no, provable guarantees. So what? Oh, and also I apologize to the physicists in the audience if these were just straw man answers. What this paper gives is a rigorous analysis of an algorithm based on something called the renormalization group method. So that's what RG stands for. And this has been a very powerful technique in physics for understanding physical systems. And for a long time, people didn't understand why it worked so well. And this paper sort of builds on a sequence of recent works showing that actually, if you develop algorithms based on this RG method, you actually get polynomial time algorithms for understanding quantum systems. That's the first one. The next one is called the Flow of Information in Interactive Quantum Protocols, or Cost of Forgetting. And this paper is about quantum communication complexity. So the setup here is, you have two parties, Alice and Bob. And Alice gets some input x, Bob gets some input y. They want to compute some function f of xy. And to do that, they have some conversation. Okay. And what people have been interested in for a long time is, well, can we show that some functions require a lot of communication in order to compute it? And here we want to say, well, what happens if Alice and Bob exchange qubits in order to try to solve this function, right? And can we show that some functions admit either a quantum speedup or savings in terms of the communication, or they're still hard, even with quantum communication? So classically, a very useful notion that has come out is, well, instead of just studying the communication complexity of problems, maybe we can study something called the information complexity, where here you try to measure not how many bits or qubits that are transmitted between the two players, but how much information they reveal to each other about their inputs. And it turns out that if you understand the information complexity of a problem, this actually lower bounds the communication complexity. So this has been very useful for proving communication complexity lower bounds. And for a while, it wasn't clear if there was an analogous notion in the quantum world. But in 2014, one of the authors, Dave Touchette, gave what we think is the correct definition of quantum information complexity in a very nice work. But one drawback is that this definition is quite unwieldy. It's kind of hard to understand. So what this paper does is it clarifies or gives a different perspective on this notion of quantum information complexity. And it tells us that we can think of the quantum information complexity of a protocol as measuring not only the information that you reveal to the other player, but also the information you forget. And this is one of the strange features of quantum mechanics, is that you actually get charged for forgetting information. I mean, normally you think that, if you want to forget something, you just forget it. But here, it matters. You have to account for it. And in fact, this forgetting is necessary if you want to get quantum speedups. So I think the right reaction to this fact is, okay. So the next talk is called Overlapping Qubits. And probably a lot of you are wondering, what is a qubit anyways? And this is a question that this paper examines. And traditionally or mathematically, n qubits is described by a vector in this tensor product space. And this is a space that has 2 to the n dimensions. Okay. But why do we model qubits like this? And implicitly, there's some independence assumption, which seems reasonable. If you have n particles, they all seem to be independent of each other. But if we really want to understand whether nature is an exponential place or not, we really have to try to see whether this independence assumption is justified. So what this paper analyzes or examines is, how do you have access to a qubit anyways? How do you know a qubit is there? Well, you perform some measurements. And I guess one way of summarizing what their paper says is, natural ways of probing for qubits can't guarantee that maybe these n particles are actually independent of each other. And they give a scenario in which these qubits might overlap in some sense. And if you have n overlapping qubits, they can live in a much smaller dimensional space. If these qubits overlap with some small epsilon, then they can all live in some n to the 1 over epsilon dimension, which is very far from 2 to the n dimensions. And it makes you wonder, well, maybe we don't live in an exponential sized space. And finally, there's this paper called Quantum Recommendation Systems. And one of the things that quantum computing and quantum mechanics tells us is that nature seems to be doing exponential sized linear algebra natively. Just when it wakes up, when it gets lunch, it's doing exponential sized computations, so it seems. And because of all the exponential sized linear algebra that we're trying to do in machine learning and big data, it seems natural to say, well, let's put nature to work then. Okay. And a few years ago, there's this paper by Harrow, Hasidim, and Lloyd that said, well, let's try to really, let's put nature to work and have it try to solve exponentially large linear systems in polynomial time. Okay, so if you walk up with a linear system ax equals to b, you want to solve for x, and a is some exponentially large matrix. You want to solve it very quickly, and in some sense they say you can, but with a couple of caveats. One caveat is that you can only get a random entry of, you can get this vector x, but x is some quantum state, and you can only access a random entry of the solution vector x. Okay, and so in one sense, have you really solved this exponential sized linear system? Another caveat is that there's a polynomial dependence on the condition number of A, and this is necessary. And so it's not clear whether you can find natural classes of linear systems where the condition number is not too bad. So after this algorithm, people were wondering, well, sure, you can do this, but can we actually really use it for any naturally motivated problem? And this paper arguably gives the first demonstration of this. What they show is a quantum algorithm for a natural or well-motivated machine learning problem that's exponentially faster than any known classical algorithm. And it's, it solves this so-called Netflix problem or recommendation problem. If you have product preferences for end users, sample a good recommendation in polylog n time. Okay? And they give a very nice algorithm to do this. And what's really notable about this result is that there's no dependence on the condition number. Okay. With that, our first speaker is Zeph.